Thank you. So thank you, Sarah, and thank you for the invitation. It's a great pleasure to tell you a little bit about my research. So I work in the quantum light and matter group in the department, and we specialize on atomic physics, essentially, atomic and molecular physics. And so I'm going to tell you about today our research on creating and controlling ultra-cold molecules. And if you are Twitter inclined, you can follow me on Twitter, and every so often you will get an update on what's happening in the lab that way. So let me begin with a little bit of motivation for our research. So really what we'd like to do is be able to understand the physics of what I'm going to call a many-body quantum system, okay? And all this means is a large number of interacting particles that are governed by quantum mechanics. And this is a very hard problem, right? But actually it's a very important problem, because if we could understand such systems, then we could engineer new materials that harness this complex quantum behavior. So to give a few examples of how quantum nature comes to the fore, these are very simple examples, which I'm no doubt you're somewhat familiar with. So superfluidity in liquid helium, superconductivity in certain materials, and perhaps one that you're less familiar, but again, the same kind of principles is the phenomenon of Bose-Einstein condensation in a gas, okay? And what these have in common is that the effects of quantum mechanics become visible on the bulk properties of the matter, okay? And obviously some of these phenomena are incredibly useful, like superconductivity. So let's look at that one in a little bit more detail. So there's a huge drive to develop high temperature superconductors, okay? But actually people don't really know how they work. And it's a little bit trial and error. And this diagram, which I've shamelessly stolen from the internet, gives you a sense of why they don't know why it works. Because what's happening is the electrons are behaving in a superconductivity way in this complicated structure. And so we need to understand these kind of complex materials, but they're very hard to calculate. And I can illustrate why it's hard to calculate and again, a very simple way. So if I think of a spin half system, which is like an electron, it can be either spin up or spin down. Then if I have two particles, I've got these 4 states. 3 particles, I have 8 different states, and superpositions of those, of course. So for n particles, I have 2 to the n states, right? So this rapidly grows to the state where you cannot simulate it on a classical computer, right? You just need too much memory to encode the quantum nature of the system, which is why we can't solve problems like this. Okay, and this very famous physicist, Richard Feynman, he understood this, right, way back in the 1980s. And there's this beautiful quote. He said, "Nature isn't classical, damn it. And if you want to make a simulation of nature, you better make it quantum mechanical. And by golly, it's a wonderful problem because it doesn't look easy," right? So what he's getting at here is don't try and solve the problem on a classical computer, because that won't work. Build a quantum simulator, right? Build a quantum system to solve your problem, right? That's all it is. So I could define a quantum simulator, if you like, is I find another controllable quantum system in which I can implement some model, which I believe to capture the physics of the real system. And then I let that model evolve on my quantum system, and I just measure what happens. And I compare what I observe with what I see in the real system to test whether that model is right. And so at some level, my quantum simulator is solving my quantum model for me without me having to put it onto a classical computer. And you can see, I'm going to illustrate how you can do that very easily. So this is a very simple model of an electron in a metal. Okay, so the electron experiences a periodic potential associated with the nuclei in the metallic crystal. Okay, Well, I can do the same thing. I can make a standing wave of light. So they just interfere lasers, and I create a standing wave. That creates a periodic potential. And then I could put cold atoms into it. And there, you know, if you look at these two diagrams, they're the same. My cold atoms experience a periodic potential. They're looking just like an electron in a metal. But now this system I can control and measure in a way that I can't easily measure and control the electron in the metal. So that's the idea of building a quantum simulator. And what I want to convince you of is that actually if you could do this with molecules, it would be even better, right? And why is that? Well, molecules are just much richer than atoms, okay? Your basic atom is a sphere, whereas a molecule has some internal structure. It vibrates and it rotates. If you pick the right molecule, i.e. one with two different atoms, it will have an electric dipole, and that will give rise to a long-range interaction between the particles, which is not present in atoms. And at the same time, it will couple to electric and microwave fields. So people are very excited about molecules, right? Bringing them into this ultra-cold regime. And so they have applications in precision measurement. There are fundamental physics measurements you can do with a molecule that you can't do with an atom. We're going to talk about quantum simulation a little bit more. Closely related to that is quantum computation. But also, you know, even a diatomic molecule is the first step towards chemistry. So we can understand chemistry from very first principles by studying ultra-cold molecules. So what we want to build, actually, so I've been in Durham since 2004, and we've been working on this problem, so it's not easy. But what we want to build is this, right? It's an optical lattice, and it's filled with molecules, diatomic molecules. And as I've mentioned, these molecules have a dipole moment. One end is, you can think of as positive, the other end as negative. And so they interact across this optical lattice. So this molecule doesn't just interact with this one, of course, it interacts with all of its neighbors. And sometimes you can even interact with the next nearest neighbor. So this is a very complicated quantum system, right? We have interactions that are spread throughout. And this is exactly the many-body quantum system that we struggle to understand, okay? So this interaction is a dipole-dipole interaction. Don't be put off by the maths. All it means is it drops off as the distance cubed, and it depends on the size of the dipole, but also the orientation of the dipoles, okay? So you get this kind of for free with a molecule, and you don't have it with an atom. The molecules, in addition, have this beautiful ladder of rotational states. So I can make my molecule rotate, and all of those energy levels are quantized. So I could use two of those, just two, and I could treat that as a spin up and a spin down. So if I encoded information like this, and I can flip these spins with a microwave field, then this lattice actually becomes an array of spins. So that's perfect for simulating quantum magnetism, which is basically how spins interact. Or you can think of this as a qubit. For those people that have learned a little bit about quantum information processing or quantum computing, this is a way of implementing quantum computing, okay? And to get these long-range dipole-dipole interactions, you actually have to do something. So one way is to use the fact that there's a transition here. And the way that manifests is if I have a spin down next to a spin up in this lattice, then naturally these spins can hop around because of this transition between the two states. Okay, so if I just wait, this state will evolve into this state. So these are called spin exchange interactions and happen in this lattice. I can also apply electric field, okay, and this will orient the molecular dipole. So this gives me control of this angle. And it also produces a lab frame dipole moment. So and these are just plotting out the dipole moments for the different rotational states seen in this diagram, just these first four, actually. And so in this way, I engineer a very complicated system, but one in which I have full control. Okay, I can control these dipole-dipole interactions. And I'm not going to talk you through this, but these pictures are just to emphasize that there's many problems one could solve with this kind of system if you could build it. So this is a class of problems that you can solve if you allow the molecules to move around in this lattice. Okay, and they're all related to superfluidity. And the TJ model is connected to superconductivity. And then if you pin the molecules to the lattice, you have these models of quantum magnetism. And this diagram emphasizes that actually, of course, with molecules, you have an almost endless degree of complexity. I mean, so far I've focused on this one, but the molecule can get more and more complicated. I can even go to a polyatomic molecule. And if I do that, the models I can test become more and more complicated as well. Okay. So you think, wow, that's just amazing. But how do you make an ultra-cold molecule? In fact, what is ultra-cold? Okay, so I'm going to tell you how you make ultra-cold atoms, because that's straightforward comparatively. Okay, so our starting point, so this is a logarithmic thermometer, and we're going to start with a room temperature vapor of an atom like rubidium. And our first step is to use laser cooling. Okay, so this is the process where we use laser light. This is what this diagram is meant to show. And we scatter photons, and each one of those photons transfers a small amount of momentum to the atom. And if you do that cleverly, you can actually cool the atom from room temperature down to below 100 microkelvin, above absolute zero. Okay, so this is a remarkable process and works phenomenally well. Okay, so well, in fact, that these three guys, Steve Chu, Claude Cohen-Tanuji, and Bill Phillips, got the Nobel Prize in 1997. Okay, so let me show you how you actually do this in practice. Right? So these are photographs from one of my labs. So we start out and we build a vacuum system. So the experiment happens in this glass cell. And this you can think of as the ultimate thermos flask. All right. So inside here is incredibly vacuum that insulates our atoms from the room temperature environment. Right. We then build some coils. So this is an assemble of copper wire, which generates all the magnetic fields we need for the experiment. And then the slightly hair-raising part is when you have to slide these coils around your glass cell. Okay, so it fits in there. And then you surround the whole thing with optics and lasers that deliver all of those laser beams that you need into this glass cell. Okay, and that gets us down, as I say, to about 100 microkelvin. But ultimately, this presence of the laser night limits how cold you can get. So we then use a very simple trick. We turn off all the lasers and we put the atoms into a conservative trap, which, for example, might be a magnetic trap, as shown here. And then what we do is we selectively remove the hottest atoms. Okay, and this, if there are collisions, and I'm going to introduce this parameter here, A, which is a scattering length. So our collision cross section is proportional to this scattering length squared. If there are nice collisions, the gas will then rethermalize to a lower temperature, and we just keep doing that, and we get colder and colder and colder. So this is nothing more than the same process by which your cup of tea or coffee goes cold. It's just evaporative cooling. And if we do that, we can get all the way down to temperatures where the atoms start to behave like waves. And when they behave like waves, they can form something called a Bose-Einstein condensate, okay, where they suddenly become quantum mechanical in nature. I thought it would be fun just to put some other temperatures on here. So this is the temperature of outer space, cosmic microwave background, about 2.7 Kelvin. This is the temperature of the sun, and the internet reliably informs me that this is the temperature of a nuclear bomb. Okay, but comparatively, these guys live in quite a small range, and it just emphasizes how far we go in the many orders of magnitude in getting down to this quantum regime. And then interrogate gas, it's very simple. We take a photograph. Okay, so we shine on some resonant light. That makes a shadow in the beam where the photons are scattered, and we image that onto a camera. And this is our camera in the experiment. So the probe light comes along this cell and is imaged onto this camera. And we actually take pictures of the gas. And they look something like this. Okay, so this is a very famous image from 1995. It's the first observation of Bose-Einstein condensation. So this is effectively a momentum picture, but it's showing you this is a thermal distribution. So the gas is let to expand, and you measure the distribution of atoms. Okay, so here it's thermal, but you see a stark difference when you move going colder in this direction. So here we see the emergence of this nice peak. These are atoms which are actually in a Bose-Einstein condensate. So they're in the lowest quantum state of the trap. And actually they're completely coherent. And if we cool further, we can end up with a pure BEC. Okay. So this is a coherent matter waves. And just in the same way that the laser is a source of coherent light, this is a source of coherent atoms, effectively. And this has really changed atomic physics. Okay, so many experiments have happened using these Bose-Einstein condensates. So by analogy with the laser, you can make atom lasers. So this is a beam of coherent atoms. It's actually a nonlinear system, so you can do clever nonlinear optics type things. So this is 4-wave mixing. This gas is a superfluid. Okay, so these are images of vortices. So if you spin this gas up, you can make vortices in it. But these are quantized vortices, and they form these lovely lattices. And this is the beauty of this field, is, as you can see, we can just take photographs of this. And this is the Mott insulator transition is something that happens in lattices. It's very hard to see in condensed matter materials, but it's very easy to see by loading a BEC into a lattice. Okay. And this all comes from the fact that we just have amazing control at such ultra-cold temperatures. And not surprisingly, there was a Nobel Prize for this as well. So these Eric Cornell, Wolfgang Ketterle, and Carl Wyman got the Nobel Prize in 2001. And I was lucky enough to work with Eric and Carl when I was much younger, before they got the Nobel Prize. So these days, we actually can build experiments where we have complete control over atoms, right? So this is a picture of what we call a quantum gas microscope. So those atoms are loaded into an optical lattice, and we use high numerical aperture lens to image that lattice. And this is actual photograph of individual atoms in this lattice. And more than that, you can use this same lens to put in an addressing beam, and you can address individual atoms. Okay, so there are ways of removing atoms from this lattice. And these are images that this group in Munich have done, where they've written patterns of atoms into the lattice. So we really have control over individual atoms. So now we can confine atoms in designer potentials. We can control their motion, even at the quantum level. Okay. We can control their internal state with either microwaves or RF or optical fields. As I'll show you, we can actually even control the way two atoms collide. And we can all do this at the single particle level, right? We can see individual atoms and manipulate individual atoms. So this is all wonderful. Unfortunately, it doesn't really work for molecules, okay, which is a bit of a pain. And I'll explain why, right? And it comes back to the fact that what makes molecules so wonderful is that they vibrate and they rotate. So this diagram gives you a sense of the energy scales in a molecule. So their binding energy is typically in Kelvin, thinking of it in terms of temperature, it's 10,000 Kelvin. And then they vibrate and they rotate. Notice this is in the microwave domain, which is why I was telling you about changing rotational states with microwaves. But actually the temperatures we're working with are way down here at the microkelvin. So there's a huge, 10 orders of magnitude energy scales. And I want to show you how this vibration and rotation manifests itself. Okay, so this is an energy level diagram of the rubidium atom. Okay, it actually, I admit it looks quite complicated, but this energy scale is enormous. Okay, so this transition at 780 nanometers is the one we use for laser cooling. And the important thing about it is it's closed. So if I drive a transition here, the atom decays back to the ground state. So I can scatter many photons, and that means I can slow the atom down. The nearest transition is this one, but it's actually, if you read this, it's about 15 nanometers away, which is a long way. It's like forever away. And all of these other states are just, you can forget about them. So let me show you a spectrum of a molecule. And actually the first molecule I worked with was iodine. And there's actually an atlas which shows you the spectrum of iodine. And I wish I could show you this book because it's amazing. It actually comes in about 3 volumes, I think. And each volume is about an inch thick. And it is just page after page of spectra like this. And actually in my PhD, I studied one of these lines. So this is just 10 inverse centimeters to give you a comparative scale. And even one of these lines has structure. So this is just looking at one of those features, zoomed in even further. Okay, and this is all because the molecule vibrates and rotates. And each quantum of vibration and each quantum of rotation is another energy level inside the molecule. Okay. So basically, in molecules, there are almost no closed transitions for laser cooling, which means that vital first step in getting into this ultra cold regime, temperatures of about a microkelvin, just doesn't work. Okay. So we have to be a little bit clever, all right? And that's what we do in Durham. So what we do is we actually say, okay, well, we can't cool molecules, but we can cool atoms really well. So let's cool 2 lots of atoms, some rubidium atoms and some cesium atoms, and then mix them and put them into a lattice where I have 1 atom of each species per lattice side. And then I'll do some kind of magic and I'll just bond them together, right? I'll just do some chemistry and turn those pairs of atoms into molecules. And that way I get around the problem that I can't cool the molecules, okay? And this was actually proposed in 2002 and is what I thought, oh, that's a great idea. I'll move to Durham and do that. I moved here in 2004 and well, we're now 2020 and we're still working on this problem. Theorists have it easy, okay? So I think at that point, what I'd like to do is just pause and see if there's any questions on what I've covered in terms of the motivation and the background before we get into the nitty-gritty of how we do this magic step.
So yeah, feel free to either ask you can unmute yourself and ask questions, or you can also pop them in the chat. So yeah.
How are you able to take photos of these with lasers and without reheating the atoms again, given you've just laser cooled them down? Surely imaging them would then heat them back up.
So that's a very, very good question. So the way I described it, it would destroy the sample because I would be looking at absorption. But there are techniques whereby rather than looking at absorption, you look at the refractive index of the gas. And these are referred to as non-destructive techniques. It's probably a slightly an exaggeration, but they're minimally destructive. So it is possible to image a gas and leave it somewhat unperturbed such that you can still experiment on it. And at the very end, I'll show you some images where we do exactly that with individual atoms. Yeah. That's a good question.
I was going to ask the same question with regards to like disrupting the system by taking a photograph, but also how do you like maintain the ultra cold states?
Maintain in what sense? What do you mean?
Like, I mean, it's between, because you start off with laser cooling and then you go into this evaporation state.
Yeah.
How do you maintain the temperature switching from one to the other?
So, so there is some heating when you transfer. So the laser cooling happens almost in free space, and then when you transfer it into a trap, it does pick up some potential energy. Okay, so the atoms, obviously, you just drop them into a bowl, and then they start sloshing around a bit, and they do pick up a little bit of energy, but not so much. So they might, you know, maybe with laser cool them to 10 microkelvin, and then they might heat up to 50 microkelvin or so when we heat them up, when we drop them into the trap.
Mm-hmm.
The key to getting to the, so people are often think, well, where's all the cryogenic stuff, right? And the magic is that actually the atoms are just held in vacuum. So the vacuum we make is phenomenally good. I mean, it's way better than anything in outer space, right? And so we can levitate, we can trap the atoms inside that glass cell, and there is just nothing between them and the walls. And so they're perfectly insulated. And so actually, you know, we can make a BEC and it'll last for 10 seconds, just sitting held inside that glass cell. There is always some heating, some technical problems, but you know, it's really quite amazing that you can be a few centimeters from room temperature and not have any problems because of the vacuum. Yeah.
Oh, brilliant. Thank you.
Yeah.
How many atoms are you dealing with at a time when you're sort of cooling them down?
So we typically start, so the laser cooling can gather up to about 10 to the 9 atoms. And the evaporative cooling, of course, you have to throw atoms away because you're removing the hottest ones. And so typically at the end, you've maybe down to about 10 to the 5, or maybe a few more when you reach the BEC transition, which doesn't sound like very many, but what really matters is that the temperature and the density, and particularly something called the phase space density, which is a bit of an amalgamation of the two, and that really determines how quantum the system is. And you can of course work with fewer atoms, and if you have detection techniques that can detect one atom, then you know 10,000 is a lot. To give you some scale, in terms of solving quantum many-body problems, classical computers can, I think, handle up to about 50 particles, 50. So even if you had a lattice that only had 1,000 atoms in it, that is way beyond what you could calculate classically for certain types of problems. Yeah.
Okay, thanks.
What is your so in the slides much earlier, when you showed diagrams of these many body systems, you showed them on like a sheet, but
yeah,
is that just a visualization tool? In reality, are they in a 3D lattice, or because
it's a 3D lattice? Yes.
Okay.
So so what that is trying to demonstrate is interfering 3 laser beams in all 3 directions, and so you create a 3-dimensional crystal. And that's one plane of the crystal. And that egg board, kind of egg box type structure is actually how the potential looks in one plane. But of course, there's another dimension where there's confinement as well. So it's hard to draw, but it gives you a sense of what it looks like. Yeah.
Do you have any issues with boundary conditions at the edge of this crystal?
Not really, because there's usually some underlying harmonic potential, so it actually smoothly goes to the edge. I mean, actually, there are a lot of interesting problems where you look at edge states, so it can be an advantage. I guess the point I want to emphasize is you can engineer that potential however we like. Yeah. Okay, shall I move on?
Yeah, and then we can like ask more questions at the end.
Yeah, good. I'm conscious that we've already taken quite a while, so we'll see how much of this we get through. But what I want to try and tell you is how we do that magic step of turning a pair of atoms into a molecule. I'm going to start by going back to that collision parameter, which I call the scattering length, and explain what that is. Okay. So my atom, I have to think of my atom as a wave, right? Because it's very cold. And so this is how I think of an atom. It's just got some de Broglie wavelength associated with it. And I'm going to put another atom at the origin. And that leads to an interatomic potential. So think of this as the internuclear distance, and one atom is moving closer and closer to another one. Of course, here the wave function has to change. It looks like this. I get lots of fast wiggles. Okay? But out here, let's see, if I just look out here, then all that's happened is there's a phase shift. Okay, and that phase shift I can write like this with some wavelength, some wave vector associated with the wave, and a parameter a, and that is the scattering length. So that was how I would calculate the scattering length. And it's sensitive to the potential in here, the depth of it, because that determines how many wiggles there are. Okay. And as I said earlier, I can think of this scattering length, if I think of it squared, that's like the cross section for atoms colliding. Okay. Now that diagram, I draw that diagram because you can see everything, but it's not very accurate. So this is a more accurate diagram. Actually, this de Broglie wavelength is very long, so kind of 100 nanometers or more. The scattering length's about 5, and the potential only about 1 nanometer. And so you see that the scattering length is this asymptote, effectively this intersection of the long-range wave function. Okay. Now, if I change the depth of this potential, okay, I'll do that. You see where this intersects changes. Actually, it's become negative now, and so I can have a negative scattering length. But that, if you think of that as a phase shift, that's fine, right? Because phase shifts can be positive or negative. That's no problem. And the scattering cross section depends on the scattering length squared, so that's no problem either. That's still a real quantity. Now, if I keep making the potential deeper, watch what happens. Now I've gone deeper to add another bound state, and that means I'm adding another node in this wave function in here. And the scattering length suddenly flips from being large and negative to large and positive. So that's another way of drawing that. The scattering length just depends on this last bound state. So as I move that bound state around, if I move it closer to threshold, the scattering length gets bigger. At threshold, the scattering length actually diverges, and then it flips sign. Okay. So if I could control where that bound state is, I could control the scattering length, right? Now I can't stretch this potential, right? It's just something that's given by nature. But something else that's given by nature is if I zoom right in, all of my atoms, all of these alkali atoms have some hyperfine structure. And this is typically a few gigahertz. So this is a copy of the same potential, but just with the atoms in a different spin state. Okay? And in this copy, there can be a bound state, which is quite close to this threshold. So if my atoms are colliding on here, ordinarily they wouldn't know about this. But if I add a magnetic field, I can shift this level around because it has a different spin, different magnetic moment. And if there's a change in spin coupling, then I can couple in some of this bound state. And in doing that, I change the scattering wave function. Okay, so So this is how it works actually. So the parameter is the magnetic field. And what I'm going to do is I'm going to turn up the magnetic field. You're going to see this bound state shift. This diagram plots the atomic threshold, that's where the atoms are colliding, this black line, and the energy of this molecular bound state. And you see that they cross at a certain magnetic field. And at that magnetic field, the scattering length becomes large and positive and then diverges, okay? So if I run this slide, you can see that happening as we scan the magnetic field. I'll do it again. Two reasons. It took me forever to make this slide. And after I'd made it, I realized there's about 3 things that you need to watch at the same time. And even with 2 eyes, that's hard. So you see, we get this divergence as these 2 states cross. Okay, and notice I put some dashed lines here. That's because actually we get an avoided crossing. And that avoided crossing happens because there are coupling between these 2 states. Okay, so whenever we get a coupling in physics, we get this kind of avoided crossing. So this is a real Feshbach resonance, right? In rubidium-85. These are the hyperfine quantum numbers. Don't worry about them. The picture is the same, right? There are 2 channels. One is where the collision is. One is where this bound state is. And this is what happens to the scattering length as a function of magnetic field. So at around 160 Gauss, there's this resonance. It has a very simple functional form. There's a pole at a particular field. There's some background scattering length, which is what this potential would give in the absence of this resonance. And there's some width, okay, which is delta. And in this case, this width is about 11 Gauss. So what that means is I can dial in, just by changing the magnetic field in the experiment, I can dial in a particular scattering length, okay? And I want you to think about that for a moment, because this is kind of amazing, right? I can actually control the way 2 atoms collide just by changing a magnetic field. So fundamentally, I can make atoms not see each other by setting the scattering length to 0, and they never collide. Or I can make it very big. And that's what we do in this experiment. This is an old experiment from many years ago now. And this is manipulating a BEC. So this is a Schrodinger equation that governs the BEC. And it's this term which is interesting. It depends on the density of the BEC, which is this bit, but also the scattering length. So if I change the scattering length, this mean field term changes. And what you're seeing here is the scattering length is becoming larger and larger, and it's causing a repulsion of the BEC, and the BEC is getting bigger. This is a photograph of it. And this is an experiment where we go to a negative scattering length, and actually we make a soliton, a non-dispersive wave packet, where the negative scattering length is an attraction now between the atoms rather than a repulsion. Okay. So that's how scattering lengths work, and this resonance is called a Feshbach resonance, and it's also connected to how we make molecules. And I'm going to go back to this picture. So this was one of the pictures I showed. There's an atomic state and a molecular state, and they cross at this resonance. It's an avoided crossing. Okay, so if I sweep the magnetic field across this, I can follow this avoided crossing, and actually I can end up in this molecular bound state. And that's how I get into the molecular world. So I'm going to show you, actually prefer to show it like this. We put the atomic threshold at 0, and the molecular states come up and cross it. So this is another one of those diagrams, but for cesium now. Okay, so this is the atomic threshold. These are the bound states that come up and cross that threshold. And this is the energy of those bound states in megahertz. Okay, so it's not very much in terms of binding energy. They're very, very weakly bound, but they are molecules. Okay, so this shows an experimental sequence where we make molecules by sweeping across this resonance. So very simply, we just start here. We sweep the magnetic field across this resonance, and that couples us into this molecular bound state. We then turn off the trap, which is this, and we apply a magnetic field gradient, which separates the atoms and molecules because they have different magnetic moments. And then the important thing to remember in all of this is we break the molecule apart and image it again, okay, to be able to see the atoms, because we can't see molecules for the same reason that we can't laser cool them. So this is what this experiment looks like, right? So here I'm applying a gradient. This is the cloud of atoms, and they are slightly over levitated. So as I drop them, they go up, but the molecules have a different magnetic moment and they fall, okay? And as they fall, they expand, and I can measure how much they expand, and that tells me the temperature. So in this case, these are cesium-2 molecules at a temperature of around 60 nanokelvin, which is exactly the same temperature as the atoms. Okay, so the important thing is this makes molecules without any heating. Okay. Now I want to tell you how we do this with two atoms, and we go back to this picture again, and buried in there, as you've seen, is this glass cell, and we prepare the atoms in an optical trap this time. So we use focused laser beams to trap the atoms, and I'll not tell you about how we get cold, but we get down to temperatures of around a microkelvin. Now with two atoms, life is more complicated. So now I have 3 scattering lengths to worry about, right? I have a rubidium scattering length, this cesium scattering length that we've seen. So this is how 2 cesium atoms collide. But then there's another scattering length, which is how a rubidium and a cesium atom collide. And actually, this is where you want your scattering length to be for cooling. So I call it the Goldilocks zone, okay? And that's because if it's too big, the cooling doesn't work very well. And if it's too small, there aren't enough collisions, and it also doesn't work very well. So we have to do the cooling. We do the cooling here, actually, because cesium collisions are good. But you'll notice that these interspecies collisions, they're too big. And so that does cause some problems. But nevertheless, we can get down to a few times 10 to the 5 atoms at around 300 nanokelvin or so. And then, having cooled the gas, we jump up to this pair of interspecies resonances and use them to do magnetoassociation, the process is called. Okay, so we actually sweep the magnetic field. It's a little bit more complicated again. We don't just go across one resonance, because you can see what happens when we sweep across this resonance. We go into this near threshold state, which has the same magnetic moment as the atom, so we can't separate them. So we have to go all the way down to the next resonance and follow this bound state curve down to here, and then we can separate them. And that's the signal we get. Okay, this few molecules, actually it's about 5,000 molecules, it's about a microkelvin made in this state, and they're bound to 2 megahertz. Okay. So 2 megahertz is not very much, right? Let me show you what we really need to do. So the molecule we're interested in is this one, which is right the way at the bottom of the potential. So this is the chemically bound molecule. The molecule we've created is just bound by 2 megahertz. Okay, this is unfortunately in wave numbers. So one wave number is about 30 gigahertz. Okay, so you can see that 2 megahertz of binding out of whatever this is, like 120 terahertz, is nothing, right? So somehow we have to get the molecule from here to here, and that we use a beautiful bit of physics, which is as close to magic as you can get, I would say. And it's a process called stimulated Raman adiabatic passage. So the picture is this: we have our weakly bound molecule here, we have our ground state molecule here, and we could connect those two with laser fields. But what we don't want to do is ever excite this excited state. And that's because if we do that, this molecule decays everywhere, right? Because it has this vibration rotation problem. So the way this works is actually, it's this pulse sequence. So we turn on this laser first, and that prepares the system in what we call a dark state. And the dark state in this case is exactly this state. It doesn't couple to this light. And so this is the dark state. And then as we turn that laser off, so this coming down, we turn on the other laser. And let's go right to the end. At the end, this laser is on and this laser is off. So now the dark state is this state, okay? And the magic is that during this overlap, the dark state evolves. It goes from being this state to this state smoothly and coherently, and it never populates this state. So just by doing this pulse sequence, we can transfer the population out of 1 and into 3. Okay, and it's an amazing bit of 3-level physics. It's very hard, and the reason it's hard is to be adiabatic, i.e. to let this dark state evolve slowly. You have to fulfill this condition, and these Rabi frequencies are generally quite low in a molecule. And this is the laser line width or decoherence, and so you have to have a very, very good laser line width. In fact, it has to be much lower than about 10 kilohertz to be able to do this. But the two lasers involved here are massively different in wavelength. So that's a very technical challenge in addition to understanding the spectroscopy. But we can do that, and I'll not explain exactly how, but it uses this nice silver box, which inside that there is an optical cavity to which we lock both lasers. And that gives the laser line width about below 1 kilohertz. Actually, it's so low, we can't even measure the laser line width. So then, okay, there's a lot of work, about 5 years worth of work, to be honest. But having found the molecular transitions and set all of this up, you can do this stirrup, okay? And the way we do it is we turn on these pulses, just as I showed you, and this Feshbach population disappears, okay? And this is the theoretical model that says that, well, we should have some ground state population. Of course, we can't see it because we have no way of detecting the ground state. And so what we have to do is reverse the stirrup sequence and take the molecules back to this Feshbach state and dissociate them and use our atom imaging techniques. And when we do that, we see the signal come back, right? Which is when you open the champagne, when the signal comes back like this. And of course, so we're transferring with about 92% efficiency all the way down here. It's completely coherent. It doesn't heat the sample at all. So we're putting in about 5,000 Kelvin of binding energy, but without heating the sample at all. And we're going to the absolute ground state, vibration, rotation, and hyperfine of this molecule. And then we transfer back, which gives us a state-sensitive detection. Of course, we can separate out these two pulses, and we can do all kinds of experiments in this window. In particular, we can start to address these microwave transitions. Now, I can see I'm running low on time. What I'm going to do is say the molecule is very complicated. So this is the hyperfine structure of the ground state. There are actually 32 states, and there are 96 states in the first rotational state. But we can isolate those. We can drive these microwave transitions, and we can drive fast Rabi oscillation. So this is the coherent transfer of population backwards and forwards in this rotational state of the molecule. We can do all the spectroscopy. So we now fully understand this molecule. We understand it so well that we can now have a lot of fun. And that's what I really wanted to just show you. So we can do all sorts. We can transfer the population up, or we can come back down. This is similar Rabi oscillations, doing those kind of experiments. We can go up the ladder, okay, so we can use different rotational states. So this is a spectroscopy on 1 to 2, and it just shows you that it lines up perfectly with our model. In fact, recently we've gone up to n equals 6, and this is a very interesting direction because this is a different dimension. So people like to call this a synthetic dimension. You can think of this as a lattice, but in internal states in the molecule. And for those of you that have a bit further on in the course, you might have come across Ramsey spectroscopy. And this is another Nobel Prize. Norman Ramsey got this for developing a technique where you use 2 what we call pi/2 pulses. So this prepares the molecule in a superposition of 2 states. You let that superposition evolve in time, and then you do another pi/2 pulse, and you read out these kind of fringes. So this is demonstrating that we can have beautiful coherent Ramsey fringes with a few hertz measurement precision on these transitions. We understand where the signal goes, the coherence remains. And something that we're writing up at the moment, an experiment we've just done, which is rather than using these rotational states for this kind of Ramsey coherence, we've used 2 hyperfine ground states, which we can put into a trap and control the coherence of those. And this data shows, actually, this data shows that we have coherence times of over 12 seconds, which, again, I want to just stop and take a breath a little bit because I know it's very fast, but what we've done here is prepared the molecule in a superposition of 2 states. So it's a quantum superposition, exactly the kind of resource you need for these many body problems. And it survives for 12 seconds, okay, which is in anybody's frame of reference is a long time, okay. So what we're working on, just to give you a sense of other techniques in my lab, other problems. So we are building what is called a quantum gas microscope, and this will be able to image these individual molecules. And we're also a bottom-up approach. And this is where, go back to one of the questions we had about, can you image an atom and it still be there? So this uses optical tweezers to trap single atoms. So these are images of single atoms. And in this case, yes, we can image an atom, check it's there, do something to it, and image it again. So there are techniques, and this is one of them. And this is a bottom-up approach to building these arrays rather than going for this big optical lattice. Yes, and if you're towards the end of your degree, you might want to think about joining some of these experiments. So I'm going to skip the summary. I'm going to go back. So this was my teaser slide, okay, which shows actually a different experiment in my group. And what I'm going to do is end on a video that shows you inside this chamber. And so I'm going to end there and thank you for your attention. And this blob is a cloud of ytterbium atoms at about 10 microkelvin in that trap. And it's so beautiful, I just wanted to show it to you. Okay, so thank you. And I'm sorry it got a bit rushed at the end.